So, the next speaker this morning is Avi Wigderson. Many of you may not know that Bourgain is the chair of the School of Mathematics at the Institute, and he runs that department meetings, which we don't have so often, but when we do have them, he runs them with the same ease and fluency that he does his mathematics, except for there's one regular glitch, and that's Avi. When Avi explains in a bit too much detail the mathematics of a candidate that he might be proposing for membership, the chair gets completely involved in the details, and this usually turns into a big discussion between Avi and Bourgain as Bourgain tries to understand what has been claimed and what he can do and what the world record is and how he might improve it and change a problem. And the rest of us just sit and watch this, and this can last for quite a while. The result is that these meetings usually last an extra 2 hours. I must say that when we leave, Bourgain and Wigderson always lead in this very energized and good mood, and the rest of us are kind of pooped, not having followed what they were saying. Anyway, Avi is a very important member of the School of Mathematics. He's single-handedly, I think, made the School of Mathematics represented theoretical computer science and complexity theory worldwide, making the Institute, the School of Mathematics, a center in this area. He's had very important visitors, many of you know them, but he's the one who's regularly here, and it's been quite remarkable. And I would add that he's brought to us the problems of computer science, and especially people like Jean Bourgain, who's attracted to those kind of problems, which, as I said earlier, suit him very well. And the result is that the mathematics and theoretical computer science, and especially complexity, look like all one and the same thing. And in fact, the feedback is back and forth with great results going both in the direction of mathematics, providing to algorithms, and techniques from complexity, solving problems in mathematics. So, I think it's fair to say that Avi is one of the world leaders in the theoretical computer science in every aspect of that theory, and it's a great pleasure to have him at the Institute, and an even greater pleasure to have him here today to speak on this occasion. His title is Matrix and Operator Scaling. Maybe I can read it here. Matrix and Operator Scaling, and there are many applications, and I think on the original thing, there's ... and I'm sure you'll see a lot of ... Thank you.
All right, thanks Peter, thanks everybody. It's a great pleasure to be here for this occasion celebrating Jean's work and impact. And we've heard a lot in the last few days, and we'll hear more about this impact. When Peter started the introduction, I was worried that he was stealing one of my stories about Jean. I have just a couple. He says Jean was the chairman of this, our School of Mathematics here at the Institute. Actually, the story I want to tell you, which is very, I'm sure is different than all the stories you heard, is that, I'm sure that you don't think that we have too many responsibilities here at the school, but there are some administration, like the, selection of candidates, various other things. And Jean, I arrived a few years after Jean, and usually, being the chair sort of follows in succession. Every one of us does it for 3 years. And about a decade ago, it was Jean's turn, and he took it like Peter described, very, casually, and has done it well. And then 3 years later, it was my turn to do it, and I was, not looking forward to that. And he just told me, forget it. You work, running your group is probably more work than running the school. Let me continue to do it. And he continued to do it to this day. So it's a decade. And, of course, all of us are happy and grateful. We talk a lot like Jean, not only in faculty meetings, we also discuss things in the office, and there are peaks, ups and downs of activity. I don't have any paper with Jean. I think the main reason, he did solve some of the problems I suggested, but he didn't solve the ones I really wanted solved. Nobody solved them, so. He did, though, work with quite a number of my postdocs. The story that you heard from Alex Kantorovich about how afraid he was of Jean and how Peter told him to relax. You don't have to be as good as Jean to work with him. So this is typical at the Institute, and I feel that one of my important jobs here is to get postdocs not to be afraid of Jean or of Peter or of Delin. And many of them did work with Jean, had joint papers, and it's great collaborations. I decided to talk about something that's quite different than what many people discussed here. And I don't know that Jean worked on this, although at the end, if we get to it, there's a relationship to some of Jean's work and other people who talked here. And it's about an algorithm. And I want to explain to you the algorithm. I want to, the main reason that I chose this algorithm, well, one is that, of course, I'm very excited about it, and it's something that I've been working on in the last few years. The other is that it's an analytic algorithm. Most algorithms in computer science, most algorithms ever used in computers are sort of digital. And this is more like a dynamical system. And, so we have this analytic object, and it turns out to contribute a lot to lots of areas of mathematics, which to me was surprising and also exciting to get to learn about these. And these not only benefit from this algorithm, they are also essential for analyzing this algorithm. And so I needed to learn lots of things I didn't know, and I'll tell you a little bit about that today. So the algorithms are matrix scaling and operator scaling. These are both problems and algorithms. And I'll start by getting rid of the list of many applications. First, of matrix scaling, it was born with applications to numerical analysis and stability of linear systems. It has applications in signal processing. We, with my colleagues, Samorodnitsky, started getting interested and actually rediscovered this algorithm in the context of approximating the permanent function, which we will talk about soon. And later use these ideas to solve problems in incidence geometry, problems like you heard about from Larry and others, but very different techniques using this matrix scaling. So it's very useful there. And that's just matrix scaling. What I'm even more excited about is operator scaling, and I'll tell you about this as well. And here you'll see how the connections to lots of areas in mathematics is sort of really bizarre. It's that one single problem, very elementary problem that I'll introduce soon, is connected, arises naturally in invariant theory, in non-commutative algebra, in quantum information theory, and also we just discovered a couple of weeks ago, really, that it's something analytic actually has applications to analysis, which is amazing. For me, the interest in it is not satisfied yet. These are the question marks here. Computational complexity issues, which I'll explain, in particular lower bounds, which we may not get to explain, and to optimization. So one can view this as an optimization tool. In particular, if I don't have time to say it at the end, let me say briefly, this algorithm, despite what it looks like, does other things. And in particular, it solves classes of systems of quadratic equations. This, in general, is, of course, NP-hard, so you don't expect it. So it's really interesting to find out which, or what can you do with it. Similarly, it solves exponentially large linear programs. Again, something you cannot solve in polynomial time in general. So it's really interesting to understand this. So all these connections will come out of a really simple problem that I'll motivate using a very simple optimization problem, which is a perfect matching problem. So let me explain it. What's a perfect matching problem? You have some bipartite graph, like these two examples, U and V, boys and girls, workers and machines, whatever you like. You want to match them up. You want to match them up in a one-to-one fashion, right? So if you can, that's a perfect matching, the left and the right. So in the left graph, G prime, oops, what am I doing? Here, there is a perfect matching. Maybe you see it. Here are the red edges, right? You can perfectly match the left and the right edges, where in the other one you can't. So that's a perfect matching. It's just a collection of disjoint edges covering all the vertices. And I give you a graph. The question is, does it have a perfect matching, or find one? It's very convenient to represent matrices by their adjacency matrix. So, for example, the graph G here are the left vertices, the right vertices, and you have one if there's an edge between them. It's convenient because that helps you represent the perfect matching problem algebraically. A graph has a perfect matching if the permanent of its adjacency matrix is positive. What's the permanent? Permanent is here. It's just like determinant without the sign. So you sum over all diagonals. A perfect matching is, of course, one diagonal. This is one of the oldest problems in combinatorics. It's been studied in great depth and length. Two basic facts about it is Hall's theorem, which will come back to us in more complicated forms. A graph has a perfect matching if and only if it has no obvious impediment to having one. So an impediment here, you see this large block of zeros, a block of zeros whose sides add up to more than n, prevent it from having a perfect matching. It's equivalent to having a set on the left that has fewer neighbors on the right. You cannot have a perfect matching. That's Hall's condition. And this was studied for many reasons, also in mathematics, and it probably is the oldest polynomial time algorithm for a combinatorial problem. Of course, Euclid is older, but for a combinatorial problem, Jacobi was interested in it in order to, for some problem which I could describe on having to do with solving, ordinary differential equations. He needed it for calculations. And he found the polynomial time algorithm. So P will denote polynomial time. By the way, another story about Jean. So, of course, mathematicians did combinatorics and algorithms always. However, I think the last century, the 20th century, they stopped admitting it. And it's not clear who's the culprit there, maybe Hardy, I don't know. I heard several stories. You need to be loftier than doing discrete things if you are a serious mathematician. So one of my first interactions with John, we talked about this, and well, we didn't talk about this. We talked about the problem which is solved. And he said, quite casually, he said, the source of my power, this is probably something you want to write down. The source of my power is in the ability to combine analysis and combinatorics. Said there are great many combinatorialists, there are great many analysts, and I have an advantage on both because I can combine them. And he admitted it in '95 freely. It took, mathematics community. I mean, of course, we are in a different place today with combinatorics and mathematics. But he may have been the first one I heard it from so openly. So Jacobi, this is, right, oops. This, of course, 1890, right? So it's, all right, so that's a perfect matching problem. And here's a really interesting way to cast it. This was done by Edmonds, and he presented a problem that motivates the rest of the story here. So we said, okay, you can check whether this graph has a perfect matching by looking at the permanent of this matrix, but permanents are very hard to compute. We just want to know if the permanent is non-zero. But in general, computing permanent is probably hard. So he said, well, here's another thing we can do. We can put variables instead of the ones, just distinct variables. And then let's call this matrix, a g of x, of variables. And then he noted that G has a perfect matching if the symbolic determinant, symbolic as a polynomial, the symbolic determinant is not identically 0. It's a trivial observation because the variables are distinct. There will be no cancellation determinant even though there are minuses. For this particular case where all the variables are distinct, of course we know it's a perfect matching problem, so it's in P. But what he asked, he naturally went a step further and says, well, suppose there are just arbitrary linear forms in this matrix. Just linear forms, so we have some variables. All the questions I asked will be interested over any field, but most of the time we'll work with the rationals or the complex numbers. So in every entry there sits a linear form, okay? And what we want to ask is whether the determinant of this symbolic matrix vanishes. Okay, that will be the singular problem, right? The name will be singular or abbreviated to sing. Okay, that's a computational problem. I give you the linear forms. I just give you the coefficients of all these linear forms. And I ask you whether it's 0. So he asks, is there a polynomial time algorithm for this more general problem? And, for a decade, nothing much happened. And then Lovász made the observation that, well, at least if we are allowed randomness became fashionable in the 70s with the primality algorithms of Solovay and Strassen and Rabin. So randomized algorithms, randomized polynomial time is as good as polynomial time, more or less, if you can toss coins. So sure, yeah, I mean, if you allow randomization, of course, it has an efficient algorithm. Just, pick random values for the variables from appropriate range and then evaluate the determinant, the numeric determinant, and then you have it with high probability. But this question remained, and you can at this point think whether it's an interesting or not interesting problem. And then two things happened that made this problem like all important. The first was Valiant independently, but about the same time, realized that the singular problem is universal. It captures the word problem for arithmetic formulas, for polynomials. I don't know if you ever wondered why the determinant is the most popular polynomial in mathematics. It appears everywhere. There's no field of mathematics where determinants don't, appear. Well, I mean, there's a very simple explanation. Every mathematical formula can be expressed as a determinant of the same size. That's Valiant's result. So that made it more important, this symbolic determinant problem. And even more for us, the question of whether it has a deterministic polynomial time algorithm as opposed to probabilistic polynomial time algorithm turned out by beautiful work of Cabanet and Impagliazzo to imply circuit lower bounds. Circuit lower bounds, this is what you should have in your mind, is P different than NP. That's what we always, our Riemann hypothesis, that's what we want to do. Proving an upper bound, just proving that an algorithm runs efficiently, turns out, for this problem, turns out will, prove hardness results. That's pretty amazing, so we should really work on this problem. It also appears in lots of areas of mathematics. It's a question about, what's the maximum rank you can achieve in a linear space of matrices. It turns out to capture modular isomorphism and graph rigidity and lots of other problems that I will not tell you about now. It's just a very rich problem. And what we care about is whether it has a polynomial time algorithm. So now I want to tell you about the dual life of this symbolic determinant problem. So let me write it again. So we have this symbolic determinant. It's very convenient to represent it by the coefficient matrices of the different variables, right? So the input you can think of as just, M matrices, these coefficient matrices of the variables. The question is whether it's singular, and now the question is singular where? Until now, it was obvious to you that I mean the variables commute, and that's indeed what I meant. And in this case, where it's in the field of rational functions over these variables. That's where it should be singular or non-singular. That's where it lives. And as we said, we know it has a fast probabilistic algorithm, and the major question is whether it has a deterministic fast algorithm. But you can ask the question in the non-commutative case. And, well, you can ask even why should you care, but the whole point of this story is that you should care even more. Well, so, it's another question. Suppose the variables do not commute now. First of all, what does the question mean? Where are you supposed to invert the matrix? Well, obviously, in the field of rational functions over these non-commutative variables, but what it is not obvious at all. It's called the free skew field. I'll talk about it later. It's, well, the localization of non-commutative polynomials. So we'll talk about it. There is a whole space. There is a whole, field, a non-commutative field in which you want to invert this, so ask about singularity. So it's well defined. And then you wonder what's the complexity of this. Well, actually, it's far from obvious that it's a decidable problem, turns out, because of this weird field. And it was found to be decidable by Paul Kohn, who contributed a lot to this theory. I'll mention him many times later. So it's decidable. And then people worked on efficiency, and Kohn and Rethenauer proved an exponential time upper bound, basically reducing it to weak Grobner basis, to polynomial equations. So there's an exponential time algorithm. And what I want to tell you about today is that this problem, the non-commutative version, has a deterministic polynomial time algorithm. So for this case, we get it. This is the main work I'll talk about. This is joined with Gurwitz, Garg, and Oliveira. It's very recent, just a few months ago, over the rationals. And then soon after, Ivanios, Chiao, and Subramaniam found that it has a very different algorithm for all large fields. And actually, the story of the relationship may come up later. Again, we'll see if I have time. I'll focus on this result of ours, so how to get it in polynomial time. Okay, that's what we want to do. We want to test singularity of a symbolic matrix for non-commutative variables. Questions?
Why is it obvious that the non-commutative case doesn't imply the commutative case?
It's not obvious. Well, it's two different games. I mean, you can think about it. It's not like, you have to think about it a little bit, but it doesn't. It's two different questions. It should be clear that if a matrix is singular non-commutatively, then it's singular commutatively. The non-commutative rank is higher than at least as high as the commutative rank. That's obvious, but that's all you can say.
What does F nav mean?
Well, in terms of the parameters of the problem, roughly exponential in the size of the data. It can be better, but let me not go there. So now I'm going to sort of go back to this matrix scaling. So forget just for a second about this symbolic matrices. We are going back to normal matrices. And I will tell you about an algorithm of Sinkhorn from the 60s that gave birth to this idea. And analysis that I mentioned developed in a paper with Linal and Samornitsky, and then another paper of Gurwitz and Yanilos. So we have a non-negative matrix, like the adjacency matrix of a graph, okay? And our task is to make it doubly stochastic. Well, what do I mean, make it doubly stochastic? You can take another. So what are the rules? What is allowed? What you are allowed is to multiply rows and columns by scalars. You are allowed to multiply rows and columns by scalars and make it doubly stochastic. Equivalently, you are looking for two diagonal matrices. So if you multiply your matrix from the left and from the right by this, then you get doubly stochastic, namely the row sums are 1 and the column sums are 1. Or approximately 1, as we'll see. So here's an example. We saw this matrix. Well, let's make it doubly stochastic. It's actually not so obvious how to make it or any matrix doubly stochastic. And if you think about it, it's not clear that it's even a convex problem. It's not clear that you can, apply any algorithm to do it. But here's Synchron's idea. And it's a natural idea. I mean, it occurred to us also, and it's, it's an idea that is so naive that you are sure it will not work, but once you play with it, it becomes obvious that it works. What's the idea? Well, you have two tasks. You want to make the row sums 1 and the column sums 1. Well, let's take care of them one at a time. Okay, so let's make the row sums 1. Well, that's very easy. You just divide by the row sum, right? So these are already 1, and this we have to divide by 3, right? Multiply by 1/3. Good. So we took care. We made it row stochastic. Now let's make it column stochastic. No problem. The only, so yeah, these are just you multiply by 3 and.
You can multiply by positive numbers.
What? Yeah, positive. It doesn't make sense to do negative. You better. Yeah, it doesn't make sense to use negative numbers. It will not help you. But anyway, positive numbers, yeah, positive. Okay, so let's make the column sums 1. So this is the main problem, right? I mean, so the sum is 7/3, so we have to divide by this. So we do. Okay, that's interesting. Of course, we fix the columns, but now the rows are screwed up. Well, let's fix the rows, You have to. All right, so we fix the rows, we ruin the columns. Repeat, repeat, repeat. Does it converge? Well, in this case, well, this is what happens after you fix the columns enough times. Then you try to do it again. Oops. Maybe I don't have the slide, but if you do it again, then this becomes 1, and this becomes half. So this doesn't converge. This is an example. It doesn't, but I just wanted to illustrate this. So let me be a little more formal. What are we doing? We are alternatively multiplying by inverses of the row sums or the inverses of the column sums. So if I denote by R of A the diagonal matrix, which is inverse of the row sums, and C of A, the inverse of the column sums. So either we multiply by R of A on the left or multiply by C of A on the right. Iterate this some number of times. Turns out we'll do it a polynomial number of times. So we do it, and let's do it just a second for another matrix, for the matrix of G prime, just to show you a positive example. This should, just not as an algorithmic question, should be interested in when does it work, when can you do it, and when can't you do it. That was the basic problem. Beforehand, it didn't work because of that block of zeros, because of the Hall condition. Here we have a perfect matching, and if we play with it, let's not do any calculations, it turns out that this converges to so that's the limit. That you'll never reach it, but that's the limit. So let's make explicit the algorithm. We run it some number of times, and then we test something. What would we test? We test that we converge. So if we ran it, let's say the last time we normalize the columns, so the C of A is the identity, you want to test whether R of A is very close to the identity, whether the row sums are very close to 1. And just test that it's within 1 over n in any norm you like, let's say L infinity. It turns out that if it did, then the permanent is positive. There is a perfect matching. And if it didn't, after this number of steps, then the permanent is 0. So it's a new perfect matching algorithm, very different than the one, and sort of analytic, very different than the ones used in the literature. And I want to tell you why it works. And why it works will be key to telling you later why the operator scaling algorithm works. So why does it work? The analysis which we gave in this paper is very simple. You want a Lyapunov function, right? You want a progress measure that you can say, we make progress. And it's very natural, I think, to pick the permanent itself as a progress measure, the permanent of the matrix. It's really easy to see that in the beginning, well, let's say it's at least row stochastic matrix. If you started with 0, 1, I'll assume we start with 0, 1 matrix. If you start with any matrix, then you have to, let's say in rationals, You have to put in the size of the numbers, so I won't bother with that. First of all, you start with something which is at least, which is bigger than exponentially small. It's not lower than exponentially small. And then, very simple argument, AMGM tells you that it grows by non-trivial factor, 1 plus 1 over n. N is the size of the matrix. The permanent of any stochastic matrix is at most 1. That's obvious. And so you are done. In polynomial number of times, you convert. And moreover, it's very easy. And another simple inequality will tell you that if you are really close to being doubly stochastic, then it must be that the permanent is positive. So that's a very simple. So that actually proves that this algorithm is actually solving the perfect matching problem. But the main thing I want to stress here is that in a polynomial number of operations, you come to a doubly stochastic, or very close enough to a doubly stochastic matrix, which gives you meaningful information, in this case, about the permanent. This was just, so is it clear? Questions about this very simple dynamical systems, normalized rows, normalized columns. This was just to motivate. Well, it has many good reasons, but for my talk, it's much easier to present this than what I'm going to present next, which is the operator scaling algorithm that will be almost identical. Just the problem is more general, and it's going back to our symbolic matrices. Okay, so let's talk about this. Operator scaling was invented by Gurwitz about 10 years ago, and what I'll tell you about is about the analysis which he started, and we managed to, prove works in polynomial time. So what is the operator scaling matrix? So rather than operator scaling problem, rather than having one matrix, non-negative matrix, now you have a collection of matrices, just like the input to our symbolic matrix. We have m matrices, let's say n by n. We want to make them doubly stochastic. What doubly stochastic means in this setting? We will see later the motivation for it from quantum information theory. But it turns out that it's some quantum generalization of this classical problem of matrix scaling. And in quantum, quantum generalizations, usually you take diagonal matrices to general matrices. You take L1 to L2, and the rest are details. So row stochastic means that the sum is like being in, how do you call it, general position. Sum of AI transpose is identity. This corresponds, that's the analog of being row stochastic. And sum of AI transpose AI is identity, is the analog of column stochastic. It's very natural, but doesn't matter if you see it or not. That's the definition of being doubly stochastic. And we want to make it doubly stochastic. We want to make this collection of matrices, this operator, into a doubly stochastic operator. And what we are allowed is just as before. We are allowed to pre- and post-multiply simultaneously all matrices by, on the left and on the right. Now, not by diagonal matrices, but by general invertible matrices. And it's sort of obvious, if we want to imitate what we did before, that we should, take care of them one at a time. If this sum is not the identity, then we divide by it. We actually divide by the square root of it because it appears twice here. It's L2. And similarly on the right. So the algorithm, we can write it, we have to assume they are invertible, but that's more or less like assuming in matrix scaling that there is no zero row. If it wasn't, then clearly the answer is no. So also here we repeat a polynomial number of times these iterations. Either we multiply by this normalizing factor on the left or by this normalizing factor on the right. Just exactly the same, syntactically copy the algorithm. I love algorithms that to code them is just 2 lines. That's roughly my limit in coding. And now, what does it do? Beforehand, we said, we figure out whether this permanent is positive. What does it do here? Well, it solves our problem. It solves the non-commutative singularity problem. Remember, this can be viewed as a symbolic matrix. We want to know whether it's singular or not in the non-commutative case. That's what it does. You run it polynomial number of times. Let's say you are done with making it row stochastic. Then you check the columns. You see whether in some norm, what your favorite norm, it's close to being the identity as it should, right? That's what happens for doubly stochastic. You check. If yes, well, then it's non-singular. Otherwise, it's singular in the non-commutative setting. That's the algorithm. This is the polynomial time algorithm. Now, why is it? What's the analysis? It's the same analysis. It looks exactly the same. And the only difference in difficulty, or at least it's not even difficult, it's just in the amazing source of things you need to bring in order to do the final simple thing of computing this, is this bound. Here, the notion is the progress measure, which we'll talk about it soon in more detail, is called capacity. It was defined by Gurwitz, and that was really the challenge he left in his paper, to prove a lower bound, an exponential lower bound on this capacity of an operator. But after you have that, it's the same. For the same reason, AMGM applied in exactly the same way. There is a growth, a significant growth in every step of scaling. Capacity is bounded by 1 like permanent was. And also here, just to get a conclusion, if you are close enough to being doubly stochastic, then the capacity, this parameter is very close to 1, which turns out to mean non-singularity. And that's if and only if. So the analysis is the same. The only open problem was this, prove a lower bound on the capacity. And this is what we did in this work. So I want to focus on this. I just want to remind, or to just summarize a few things that this algorithm does. It actually can compute, there's an analog notion of rank for the non-commutative case. It computes the non-commutative rank in polynomial time. It actually can compute this capacity parameter. So unlike the permanent in the scaling case, for capacity, we can actually compute it for any such operator or symbolic matrix. We can also, of course, compute the scaling matrices. That's also in the previous algorithm. We just keep track of what we multiply by, and the product of them is the scaling factor.
This is one matrix. It's not the. Suppose it's just one matrix.
Yeah, it's a different definition, right? It's not the, yeah. It's L2, yeah, so it's different. Yeah, well, unless you are too close. Unless you are already close. Of course, there must be an if. Sorry, I should have said it. If you are, let's say, 1 over, if you are 3 over n apart, then it will grow by 1 over n. If you are far enough from 1, then you have room to grow, then you'll grow. If you have room to grow, you'll grow. Okay? Yeah, capacity at doubly stochastic is 1. So as long as you are away from 1, you'll grow, and then you'll detect it because we are checking that we are close or not. Okay? So we run for, let's say, n to the 10 times. We stop, we check if we are close. We can be close if and only if the capacity is very close to 1. And another point I want to make is that this algorithm, this dynamical system, is obviously continuous. It's just, by definition, you are just multiplying by things that are continuous in the data. So that will come up. Okay, so I want to talk about where the lower bound is coming from. So I want to talk about the origins of the proof of the lower bound, which I said it's simple, but it's rich. And it has these 3 fields that I'll tell you in one slide about each. And if I have time, I'll tell you about, there are, of course, applications to all these fields. There's also an application to analysis, which I mentioned, that I hope I'll get to. So I want to tell you just like highlights of each of these fields and what it brings into this problem, or how this problem naturally... I will, yeah. And how this problem naturally arises there. Yeah, the non-commutative rank of symbolic matrices arises here, here, and here. All right? So First, non-commutative algebra, and I want to talk about the word problem for this strange field I talked about, so let me say what it is. So we have this setting, we have a commutative field, normal field, or favorite field, and we also have a bunch of non-commuting variables. Okay. And polynomials in this non-commutative setting look like your normal commutative polynomials. They just have a few more monomials because monomials, the order matters. But it's, it's a simple algebra just like your favorite polynomials. And now you want to localize this algebra of polynomials, right? You want a field of fraction for this polynomial. So one natural way, and in fact that's the original way in which it was defined, unlike any algebraic object I know, it was defined by computation. It's not clear how to give a, canonical representation. So you say, well, what should it do? It should be an object closed under addition, multiplication, and inverse. So that's what you say. Well, let's allow rational expressions. Let's allow to add, multiply, and take inverse. And the minute you do it, even for the simplest expressions like this one, you realize that you are in trouble. Because this, you cannot, even this simple thing, you cannot write as a ratio of two polynomials. So this is out of the game. Some people here, of course, are into non-commutative stuff of this and realize this, but if you've never seen it, sort of bizarre, and then you start wondering, well, okay, what's a canonical representation of objects in this weird field? And yeah, it's not obvious. There are more complicated expressions. Suppose you look at this expression. This expression has nested inverses. Nested inverses never exist in the commutative case. You can simplify, right? Well, it turns out, and it's a deep theorem, it's really beautiful, Rathenau proved that not only you cannot get off nested inversions, there is an infinite hierarchy. There are expressions of arbitrary inverse height. So it's complicated, but sometimes you can. Some of you who are into projective geometry, this is a fundamental theorem of projective geometry, who has identity. If these variables are the same, if z and w were x, then this nested inversion can be eliminated. So this expression is this expression. It's a toy example. You can prove it yourself. So sometimes you can, sometimes you can. Well, which expressions are equivalent? That's a basic question. Well, this is a word problem. When is a given expression rational? I give you a formula like that. When is it identically zero? Okay, that's a word problem. It's a basic problem in any algebraic setting or any setting in general. You have various representations of the same object you want to know when they are the same. And the first one to define the free skew field was Amitzur, and to really build this big theory, said the rational expression, you want to know whether it's zero. Well, clearly you can instantiate the variables with any elements of any ring you want. So let's do just rings of matrices, but of every size. So let's plug in for the variables all possible matrices of all possible sizes, all right? And evaluate them. Well, of course, sometimes this will be dividing by zero, so it will not be defined, but whenever it's defined what you want, I mean, the obvious demand will be that it will be equal zero, this matrix, but actually what he showed, and that's deep too, it's sufficient to just say whether the determinant is zero. So that's an if and only if for testing membership for the word problem. And this is, okay, it's satisfactory, but then Kohn came and gave I would say, much more elegant and also useful for developing the theory criterion. And what he showed is a theorem very similar to Valiant, actually before Valiant, for the non-commutative setting. So if you have a formula now with inverses over this non-commutative setting, you can build from it a set of matrices, right? Just a symbolic matrix. You build a symbolic matrix. The size will not be much larger than your rational expression. And this rational expression is identically zero exactly when this symbolic matrix is non-singular in the non-commutative case. Okay, that's a theorem. And moreover, because of Amitzur's characterization, it turns out to be the following. I mean, you can still instantiate these variables with matrices, and then there's a blow-up, there's a tensor product, right? So now you look at the matrix, which is the sum of AI tensor di. You just put the variable, you make it a matrix. And the requirement is that this is identically 0 if the determinant of these blowed up matrices in every size, in every scale, up to infinity, is 0. So it's an infinite system of equations. If they are satisfied by the AIs, then the rational expression was 0. Well, let's also explain why it's not obviously decidable, right? Okay, so let's skip this. You have to remember just this expression, this determinant, right? Because it will come up. So it comes up naturally in non-commutative algebra, in the word problem for non-commutative algebra. I, of course, want to mention, because we solved this problem, we know when an expression, symbolic matrix is singular or not, we solved the word problem for this free skew field in polynomial time. So that's one application. I should say also that I mentioned we can compute the non-commutative rank. It turns out that Fortin and Rethenauer proved that non-commutative rank is within a factor of 2 of the commutative rank, which is a problem I really care about. I mean, singularity in the commutative case. So at least what it says is that you can, in polynomial time, approximate it to a factor of 2. It's really interesting. And you should do better than that. Let me move to a completely different field, which also gives us an important ingredient to the puzzle. That's invariant theory, in particular the left-right action, group action that I'll define. This commutative, now commutative invariant theory, normal invariant theory. So let me remind you very quickly, basic question. We have some linear action, so we have a group acting on a vector space, and so it automatically acts on the ring of polynomials in the same number of variables, right? It's identified as variables with some basis of the vector space. So we have an action of a group on a ring of polynomials, and the central definition object we care about is the invariant ring of polynomials. The invariant ring of polynomials is a set of polynomials in these variables that remain invariant under the group action, okay? They don't change. So just examples to remind you that you are familiar with this thing, even if you are not in invariant theory. If the group is a symmetric group on n elements and we act on Fn, then by just permuting coordinates, then this ring, invariant ring, is generated by the elementary symmetric polynomials, right? Okay, that's very good. Actually, it's generated, therefore, by just, if it's Sn, it's generated by the first n symmetric polynomials. Okay, so this is finite generation, actually, even though there are infinitely many ones. Another example, let's say, well, maybe I wanted to, so, okay. The general linear group acts on Fn, Fn squared, so on matrices. On matrices by conjugation. You just send a matrix, a group element here, B, just multiplies it on the left and on the right, this way. Just conjugation. What is the invariant? It's only one invariant. What's this? All invariants are generated simply by the determinant. So you know examples like this. You've seen this. And where the one we care about is a left-right action. And left-right action is multiplying from the left and from the right, as we already saw. A bunch of matrices. So we have a set of matrices. That's the space, the vector space we act on. So it's a space of m times n squared variables, right? All the possible variables here. The action is just by multiplying. So L, this tuple of matrices, we multiply it on the left by some invertible matrix and on the right by some invertible matrix. Okay, that's a group action. Why on earth should you care? Well, there's a big field called understanding quiver representations. Everybody knows what a quiver is. Here's my favorite quiver representations. So a bunch of arrows, in other words, a directed graph. And this particular quiver here is this directed graph. And it shouldn't be meaningful to you if you've never seen this, but I should say only that it's not an arbitrary example. This particular quiver is a universal quiver. If you understand it, you understand all others. So it comes up in lots of areas, with quiver representations in general. This particular one, I will not go into this. And I just want to tell you what we know and how it connects. So here it's, I'm repeating what I said before. Here's the invariant ring. It turns out better to study semi-invariants, namely actions by the special linear group, determinant 1. So we want to understand this invariant ring. What is it? Which polynomials are there? What generates them? And lo and behold, this is the result from 15 years ago. Even though the subject is very old, it was understood relatively recently that the set of, that it's generated by the same polynomials we saw. So if you just put variables here, first we had matrices, numeric matrices. If you put symbolic matrices here, and you blow them up by all possible matrices, D by D matrices for every D, then this set of polynomials, infinite set, generates the invariant ring of this action. So a miracle is the same, exactly the same set of polynomials. And now, unlike the previous examples where we had finite generation, you want to ask, it's natural to ask, and it was probably natural to ask even when I talked about the non-commutative field, which, do we need all these infinite, number of equations? Maybe we can do with a finite one. And luckily in this field, we have a theory. I should say, two basic questions about,
Who are those people?
Yeah, very good. Dirksen and Weyman, Domokos and Zubkov, and Vanderberg and all these invariant theories. So Vanderberg and, I don't remember. Yeah, all at the same time. The two basic questions about this invariant ring. You want to know, for example, I give you a set of matrices. Is it 0 on all these invariants? That's a special case of and this is something we can solve because that's exactly solving this set of equations. That's right, plugging A's for the Z's. That's exactly the problem we can solve. So we can solve membership in the null cone. The more general problem that we cannot solve is maybe the more interesting one about orbit intersection, orbit closure intersection, but I will not talk about this. Anyway, what do we know about making this system of invariants finite? Just finding a finite number of representative, or in other words, just bounded the degree, the dimensions of these matrices. Well, we have degree bounds. First of all, Hilbert, that's again 1890, right? In this famous paper, this is one of the most famous papers in mathematics, where he did an Ulf-Stahlen-Satz, when he did the Hilbert basis theorem. What he really wanted, well, I don't know if I never talked to him, but he's aiming it all at understanding invariance of linear actions. And for this, he developed all this wonderful theory, and in particular, he proves that there's a finite bound that generates all the invariants. So this is finitely generated. Then people started working on getting bounds. Maybe the first concrete bounds was doubly exponential. And then, very important to us, Dirksen proved about 15 years ago an exponential bound. As it turns out, I will not be able to show you how it works, but this exponential bound is the key to our exponential lower bound. And somehow indirectly, this exponential and the other exponential are not the same. This is what gave us the capacity lower bound and the analysis. And then, so I don't need to continue, but I want to tell you that this is a rapid developments as we speak. A couple of months after we did this, Dirksen and his student, Makam, proved polynomial upper bounds. And these polynomial upper bounds actually lead to the different combinatorial algorithm that I mentioned that works also for other large fields, not just the rationals. So it's very exciting. Finally, I want to tell you about quantum information theory and completely positive maps. And this is where the word operator comes from. Yeah, I will, on this slide. I will satisfy you. I will satisfy you. And you will recognize, well, some people will recognize capacity. So here, this bunch of matrices have a different life. Here they are a quantum operator. And that's how they operate on a matrix. Just you sum up AI P, AI transpose for every matrix P. And why is it called a completely positive map? Because it sends positive matrices, PSD matrices, to PSD matrices. And that's, in particular, in quantum information theory, you apply them to density matrices, right? Okay. Here's a property that Gurvitz cared about, the operator being rank decreasing. Rank decreasing if the operator sometimes decreases the rank of its input. This has some meaning in quantum information theory that I will not go into, but I want to say that this condition, this rank decrease, is an algebraic analog of the whole condition in the combinatorial case. And maybe we'll see another reincarnation of it soon. Now, Kohn, in the theory he developed for understanding the non-commutative skew field, proved lots of linear algebraic facts. I mean, he moved it into a linear algebra setting. And in particular, he proved this. It's rank decreasing if and only if it's non-singular, non-commutatively. So also we solve this problem, this rank decrease of quantum positive map in polynomial time. That's an application. We define doubly stochastic for an operator. This turns out to be very natural for a completely positive map because this means that it sends the identity to the identity, and this dual thing means that it's trace preserving. So it's very natural for quantum operator. And he proved several things, but first he defined this notion of capacity. And capacity, you look at all possible positive matrices, and you look at the ratio of the input to the determinant of the output to the determinant of the input. And you want the infimum of that. That he called the capacity. And capacity is very natural and very useful. I'll give you just a few examples. For example, capacity is 0 if and only if it's rank decreasing. So you want to compute capacity. Well, it's 1 exactly if it's doubly stochastic. And yeah, and it behaves very nicely under left and right multiplication. You can compute how it changes. And another thing, it tensorizes with some normalization that I didn't put in. I mean, I just didn't tell you what happens here. So it tensorizes, and because of that, all of that, and some manipulations, you can prove, you can use the degree bounds from the previous slide and these properties in order to prove that, the lower bound, the exponential lower bound on capacity, and therefore the polynomial time, running time of the algorithm. Okay, questions? Because I have one more story to tell. Yeah, well, I have 5 minutes. Don't look at me like that. All planned. Yeah, I mentioned this is not a convex program, so it's not clear. It's special that we get a polynomial time algorithm for it.
So this capacity was introduced by Kohn or Bourgain?
No, this by Gurvitz. So I told you this whole analytic setting gives back something to analysis, so I want to very briefly tell you what. I'm sure most of you guys are analysts. You have to know the Braskamp-Lieb inequalities introduced by Braskamp and Lieb, and then later figured out completely by Lieb. What's the setting? Well, believe it or not, it's just given by a bunch of matrices. Here the matrices are actually narrow. They are from Rn to Rnj for some numbers. And J, this is one piece of the data in Braskamp-Lieb inequality. The other is a bunch of non-negative numbers. Okay? And what is a typical Braskamp-Lieb inequality is an inequality of the following type. So this is called the BL data. It's an inequality of the following type. If you've never seen it, it looks ugly. But you just think about Cauchy-Schwarz. The integral of a product is at most the product of the integrals. Okay, so it's a very...
Yeah, I think we can complain about your color scheme. What is it?
But I'm sure you can complain. Anybody who knows Peter knows he can complain very well. So, I mean, let me, just because of time, what you want to say, what you really want to say is that for this fixed data, you have an inequality. It's a multilinear inequality. Integral of a product is at most a product of the integrals. Well, anyway, let me not say it, but it should hold for all integrable functions. You have m integrable functions from these spaces R and J to the reals, so you get real numbers on the left and right-hand side, and you want to say that they are related by this universal constant C that does not depend on the functions, like the Cauchy-Schwarz inequality. Okay, good. So here is just, if you don't understand this, here are lots of inequalities that you must be familiar with some. It's amazing how rich it is, how much it captures. Lots of these things don't look like they should fit in this framework, and they do sometimes non-trivially. I want to mention in particular this nonlinear Braskamp-Lieb because at least one connection that I don't understand, because this discovery of ours, this realization of ours is very recent. The nonlinear version of Braskamp-Lieb, which I will not explain, turns out to be related to the things that some people like Larry Guth were talking about, Cyprian Demeter, decoupling and various multilinear estimates. I don't understand how they are connected, but the papers claim they are connected, so they are connected, so I want to say something about this. So what do we know about this that people didn't know? There's this constant appearing here, well, let's give it a name, Braskamp-Lieb of the data B and P. It's some number. It's the smallest number you can put in this inequality and leave it valid. Well, when is it finite? For which data is it finite? What is it? Can you compute it? Well, we know things about it. The structural theory is very developed. We know that it's finite if this vector P of non-negative numbers belongs to some polytope, which is given by these linear inequalities that I will not read to you. We also know, but it's an exponential size linear program. We also know by Lieb, and here you should jump, that this constant, can be expressed as an infimum of a ratio of determinants. These determinants over all positive matrices. So it has an expression. Well, what can we do? So this is what was known, that there is some expression which cannot be computed that captures it, that finiteness is described by an exponentially large program. Well, what we do is actually show that this is a special case of operator scale. It's just a very simple special case. And because of that, we can compute it in polynomial time, the constant. We can optimize over this, over this polytope, so we can tell you which vectors P are feasible and which are not, all in polynomial time in the parameters of the problem. It actually, the algorithm also gives a proof of these things. Here you will recognize the whole condition, the rank non-decreasing. Here you will recognize capacity, obviously. And moreover, something that this nonlinear version, that I mentioned before, again, I'm not going to say what it is, but what's needed is some kind of continuity of this parameter, of this optimal constant in terms of the data, in terms of B. Well, they use compactness arguments to say that, well, it's somewhat continuous. It's, very, very weak statements, totally non-computable. From this work, from the very obvious continuity of the operator scaling, you get concrete bounds which are roughly best you can hope for. Where is my conclusion? Oops, maybe I don't have the conclusions. Just to summarize, I want to stress the obvious. I believe that algorithms give a huge richness to mathematics. Studying existence from an algorithmic point of view and even from efficient algorithms point of view gives new questions and new answers. It's pretty amazing to me that symbolic matrices and operator scaling fit so nicely in so many, were studied in so many different fields of mathematics. In terms of problems, let me leave them on the board. Thank you.